right? So this is more of a question about, are we using the correct boundary layer parameterizations in the Bay of Bengal? And so for motivation, I'm going to start with this image that we saw earlier today from Eric's talk from Zhang et al., which shows a quadrature relationship between SST and precipitation, highlighting the role of air-sea interaction in the meso. And then also, this is a plug for a poster later on today. This is work done by an undergraduate in our group who used the extended EOF meso index by Suas et al. To diagnose the meso and CESMs, and showed that just using different mixed layer parameterizations, you can drastically change the phasing and duration of the monsoon. And so Akash is going to be presenting that tomorrow in the poster session. And so, we care about mixed layer dynamics, and we want to make sure to get them right. And so we might think about what kind of parameterizations we want to put into our forecasting models or our global circulation models that might include waves or lateral restratification or others that we haven't thought of yet. But this is ultimately going to be based and founded on this foundation of what type of 1D mixing scheme we have. And so we want to maybe take a look at this first. And this is a little bit motivated by some work that is a comprehensive study that's being led by Ching Li at Los Alamos. And in this image, we're looking at different boundary layer mixing schemes, some just one-dimensional and others that have Langmuir, different Langmuir parameterizations in them. I'm not going to be talking about Langmuir today, but what this shows is here's a difference in monthly mean mixed layer depth from the entire mean of all the models. And what's striking about this is that these models on the left, without any Langmuir parameterization, still show a significant amount of spread, almost as much spread as you have once you add these different types of Langmuir parameterizations. And this is kind of highlighting that these different 1D mixing schemes might be giving different results. And so today we're just going to look at what this looks like for the Bay of Bengal. So there's lots of different 1D mixing schemes. I thought to narrow the focus of this talk, I thought I would just focus on several types of mixing schemes based around the KPP parameterization. So we're going to look at a KPP model that's pretty tried and true to the large et al. Paper. And then we're also going to compare it with a KPP that's implemented in ROMS, which is based on the same physics, but it has a different definition for mixed layer depth. It uses an integral approach to calculate its boundary layer, which we'll see has some impacts. And then we're also going to look at CVMix. CVMix is the new generation of KPP models that is based on KPP, but it has more sophisticated mixing and entrainment velocity that is intended to increase the model fidelity in our forecasting and general circulation models. Yeah. Yes. I do not know. Yeah, I'll have to look. Yeah. And then, and that if you're interested, we could also look at what it looks like to vary that parameter. But. And then also, I'm not going to talk about this today, but for those who like TKE models, I included results from K epsilon. And so these are all, just implemented in a 1D. These are column models, but it's going to be step forward in time using GOTM, the Global Ocean Turbulence Model, with a time step of a minute and a spatial resolution of 1 meter. All right, so we're going to use the forcing from that, this is inspired by the 2018 pilot cruise. And we've seen this before, but, and this is on the team drive. But what I really want to highlight here is that there's this monsoon onset where the winds peak, there's lots of rain. I'm guessing this is the image from Drew that we saw all of this rain from here. And then this kind of break period where the winds die down and the sun starts shining. And to make things a little bit fun, again, this is for all of the modeling teams to kind of use. We thought that we would adopt a profile that has a subsurface temperature maximum. And so I chose a profile with a temperature maximum, and I used that to create two profiles with a tanh function, one that has a temperature maximum and one that doesn't, but both of these are going to have identical density and stratification, so similar in that way. Anyway, so how do these look when you put them into these different types of models? Well, you can see that they differ quite a lot. And so on the left, we're looking at these temperature profiles, one with the subsurface temperature maximum, one without. And what we see is that the mixed layer depths change quite drastically. And really, so what was interesting about Eric's talk is that he showed PWP deepening these mixed layers and said that 1D models all get this deepening of the mixed layers correct. And we're seeing that that's precisely where all of these 4 KPP type models are starting to diverge. And so, so even though they are based on the similar physics, they're implemented in slightly different ways. And we're seeing that this is the exact time during this active stage where they can't agree. Okay? And it's actually during this stage where the rate of change of mixed layer depth kind of levels off, and they don't agree, but they're at least steady. Right. So let me label. So this is KPP, and this is CV mix. And then the purple is KPP, but this is the one that's implemented in ROMs. So it has a slightly different definition for how it defines its boundary layer depth. And I've also included the FAST-CTT data in gray in the background. And I included it for reference, but I think it's also good to note that we can't compare any of these models with the FAST-CTT data necessarily, because we don't really know what truth is here in the one-dimensional sense. I think the results from ASIRI have really shown that. And so while it is reference, you can't really say which ones of these models is true to the 1D mixing. Can we say that they're all wrong? Well, they're all models are wrong, and some are useful, I think is what Baylor likes to say. Most are useful. But yeah.
I think we can say, like, that the fact, because we had assets, that the kind of represented by the fact is kind of like what it was having over a lot of the day. Like the epsilon and the or in the realm of
Yeah, I mean, I think that's a fair thing to say. It's also, I'm not showing this here, but if you look at the shear structure developed by these, I would say that there's a problem with these models that give it more reason to not believe it.
Out of curiosity, that kind of first stratification, that kind of function fact.
Yeah, there's some sort of energetics budget that is happening right there that I haven't been able to work out. I mean, I've tried to think about it, but I haven't yet been able to figure out how to approach it. But I think what's happening here is that the bulk Richardson number definition here is not able to deepen this mixed layer. But if you look locally at the local Richardson number here, it's subcritical. So these models aren't quite working. Yeah, Amit?
Just a comment. So I know you must have done it, but I don't see.
Yeah.
The original are
Right, that's a good question. So it stands right in the middle. It's right in the middle of all of this. Yeah, it is. It is. But oh, go ahead.
I would submit that.
So, no, it's okay. It's getting there. It's getting there, and we can. I mean, we can pretty much end it here, but or like at least bring it back to this, because this is the. I think. So I think there's a lot of. Okay. So right. So. Just to wrap it up a little bit, and then we can come back to the slide and discuss it. But what I thought was interesting, the little kind of shining star about these results was that where these models stopped in their mixed layer deepening kind of decided whether or not this mixed layer was going to entrain this subsurface temperature maximum. So kind of like what Simon was showing before is whether or not the ocean is going to warm before it cools. And we can see that here. We can just look at the sea surface temperature, and in fact, these models that get deeper mixed layers are warming. And then we can play around with this, and we can estimate what that effect is on the latent heat flux, and say there's a standard deviation of 20 watts per meter squared. And then, I made these up before this discussion and before Eric's talk. So maybe it's more worth it to talk about this and its importance, which is, I think what we saw today with PWP and with Kate's results that Jen and Drew mentioned was that we don't expect this deviation to hold in all parts of the Bay of Bengal. We don't even expect that KPP is always going to be shallower than K epsilon. Sometimes it's the other way around. So in order to get a better sense of what this is, I think that maybe we're not quite done understanding, especially what these are the models that are going into our forecasting and our general circulation models. And I don't think we're that done looking at them. So I propose an effort to kind of look at this more broadly across the Bay. And if there are certain times of the year that you think are particularly interesting, or certain regions that are particularly interesting, you can let us know, and we can include that in the evaluation.
Yeah, question. Yeah, you can go ahead. You can go ahead.
So I like how you use all these different models. You have this multi-model ensemble, and you pointed out that actually the observations they're actually just sampled from an ensemble as well. So is there a clever, these are not expensive models.
No,
is there a clever way of using all of the observational assets to make an ensemble forcing set so that you can, because like you said, here this model works better, but there or on Wednesday a different model works better. It's not because it's Wednesday. We can learn a little bit more about it.
Yeah, so I think that's really interesting. I guess I've kind of done that with reanalysis and smoothed climatological profiles to run all the different and kind of get an idea of what the variance is. I was kind of interested in whether or not the variance in SST from 1D models could, how it brackets the variance in SST variability that you might get. But
use the variance in the force.
oh, I see.
Observation, so that you're not trying to aim. There's
Right.
so much unknown stuff.
Yeah, yeah. Yeah, I think that's yeah.
The question.
I think if I understand it correctly, it's understanding the variance in the observations by adding variance in the surface forcing to see if this variance in the surface forcing or lateral variability can create the same type of variance that we see here. Is that it? Yeah. I think that's a good way to.
Just a comment is that mixed layer depth is a poor measure because there's mixing beneath the mixed layer depth, and depending which model you have, the depth to which the mixing is relative to the mixed layer depth changes. So you should use a metric that's
Fine.
consistent between the different models.
Right. So let's say you use a minimum of W prime B prime, which might.
Yeah, but not all the models have that. It would. I mean,
you can calculate it from rate of change of potential energy. It doesn't change.
You want to do it? Okay. Yeah.
I mean, you can do that, and if you use, for example, if you use that metric, it doesn't change this. Okay.
Done.
Are we done?
So let's thank all the speakers again. So this concludes the session.